Students, let us start the lecture 22, and this will be extension of lecture 21, that's on thermal properties of nanomaterials. So, you know that in the last lecture we have been discussing about thermal properties, especially the thermal conductions. Okay, that's what is we have been discussing, a thermal transport. Thermal transport is very important in electronic devices, right? Electronic devices has like computers, laptop, mobile phones, etc. The thermal transport is equally important. So, there are two things which is required in while thermal transport is considered. One, that is the heat must be conducted away or heat must be taken away, or there will be situation where you need to put a barrier to the heat transport. These are known as a thermal barrier. In both the cases, important aspect is the thermal transport. So, there are few aspects we have already discussed. Let us first have some recap of those. As you know, thermal transport and the melting temperature of nanomaterials are important aspects to be considered while designing any component using nanomaterials. So, in any device, heat is transported by either electrons or holes and phonons, which are nothing but lattice vibration. So, electrons in a metal are free, they are not bounded or they are actually not localized, rather they are delocalized electrons which can move from one place to other place without much of hindrance. But hindrance can come from the scattering of electrons by different kind of scatterer like gain boundaries, or even it can be scattered by the heavy atoms. So, therefore, there will be some kind of a loss of because of these scattering events. On the other hand, phonons or lattice vibrations are more important for non-metals, where electronic conductions are not possible. So, these are actually traveling waves which are propagated to the material because of the vibrations of the atoms. So, as you heat the material, atoms start to vibrate, and because atoms start to vibrate, they push and pull each other during the vibration, and that leads to the motion of a wave or traveling of a wave in the material. And this is what is known as a phonon, which we have discussed in the last lecture already. So, in a standard material like FCC, atoms are arranged in a chain, right? Right, these ABC layers. Now, these atoms can be considered to be connected by springs, right. So, as they are connected by spring, now during heating up of the material, the atoms will vibrate from the mean or equilibrium positions. So, as it vibrate like this from both the directions, what will happen? The atom, one atom can push the other atom, or it can pull the other atom in the neighborhood, and this can lead to a traveling wave, and that is what is known as a phonon. This is shown, something is shown here. So, you have suppose chain of atoms 1, 2, 3, 4, and they connect by spring. Now, if they move small distance x n minus 1 atom, suppose it moves by small distance from its equilibrium positions, what will happen? This spring will get pushed or pulled, and this can lead to a traveling wave. That is what we are talking about phonons. So, well, one can actually design equations of motion taking three neighbors x n minus 1, n plus 1 and x n. Okay. So, central atom will be pulled by both the corner atoms or the atoms at these positions x minus 1 and x plus 1, and this can lead to a kind of a motion equation in terms of force. M is the mass of the atom, and this is double derivative with respect to time is acceleration, and this is nothing but the push and pull. So, therefore, this is the force, this is also force, and G is a spring constant, right. Hence, we can solve this equation and we can get two important exponential solutions, one in terms of t time, other in terms of amplitude or A. A is the equilibrium distance between the two atoms when they are not scattered or they are not moving from equilibrium positions. Okay. So, hence, if we plot these things, okay, we can get some sort of a scattering things like that. I do not know whether I have had here, I have shown in the last class. So, you have a two branches of the thing, this is k, and so this is omega, and this is twice pi by a. So, you have a two branches of the travelling waves, correct. So, that leads to motion of phonons from one part of the crystal to the other part of the crystal. Now, this way heat can be transmitted. So, now the question is this, whether it is an electron or a phonon, whatever may be the carrier of heat, carrier of the thermal transport ways and means of that, important aspect is what? Important aspect is the psi effect of nanomaterials on the electronic or the phonon energy levels. That is what is going to dictate or control the heat transport in nanomaterials. So, before we discuss that, let me just tell you again that as the nanomaterials have different dimensions 0, 1, 2 or 3. Therefore, the electronic energy levels as well as the phononic energy levels can get affected significantly by these dimensions. You may ask why. That is very simple. As the dimension of the materials becomes small enough to be comparable with the electronic energy levels or the phononic vibrations wavelengths, what will happen then? Then they will interfere each other. The dimensions of the material will interfere the energetics of the electrons as well as the phonon wavelengths, and this can significantly affect the thermal movements. So, how does it happen? Let us talk about it. That is where the important aspect comes into picture. Okay. What is that? That is what is known as the confinement effect. Okay. So, as you know, in a material, you have antibonding and bonding orbitals, and electrons are divided between conduction and the valence band, right. And each band has a width that reflects the interaction between the atoms with a band gap between the conduction and the valence bands that reflect the original separation of the bonding and debonding states, right. This is the band gap. So, in a metal actually you do not have any band gap, right. There is no band gap between in a metal because the valence band and conduction band overlap each other. On the other hand, in semiconductors insulator you have a definite band gap. So, in a semiconductor band gap is small compared to the insulators. So, therefore, because there is no band gap between the conduction and the valence bands, what will happen? Because of overlap of these two bands, electrons are free to move. There is no barrier, and as you see, because there is no barrier, so electrons are delocalized. This is we have discussed about it. But in a semiconductor, you need a definite energy gap between these two bands, and therefore, we need to provide that energy to the system so that electron moves from valence band to the conduction band. This can be done by using heat or thermal energy or by doping, right. We can modify the band diagrams simply by doping. In an insulator, you can't do that. There is no electronic conduction is possible in an insulator. So, there only heat conduction is possible is a phonon. Let us think of electronic insulator like diamond, but diamond is a good thermal conductor. So, therefore, in a diamond, phonons actually are the major heat carriers, correct. So, what are the situations? Both phonon and electrons can undergo confinement. Why? How does it so? So, in a metal, as you can see, the bulk material, electron, this is what is shown here, the conduction band is completely full, and the valence band is completely full and conduction band is overlapped with the valence band, right? That's what is shown there. The highest energy level is known as a Fermi level. That can be seen from here, which is the completely filled energy level. So now, as you decrease the dimensionality of the material, that is what you make a nanomaterial of that, these bands will undergo discretization. That means these bands will no longer remain continuous. As you can see here, density of states is varying continuously with respect to the energy E, right? For the 3D nanomaterials. In 3D nanomaterials, all the dimensions are not nanoscale. They are bigger than the nanoscale dimensions. So, as soon as you make them as a nanoscale dimensions, any of these x, y, z directions, what will happen? The energy levels will undergo discretizations. You might be thinking why it is so. We will come to it very soon, why it is so. Energy levels will be discretized, and that means what? Electrons cannot occupy any energy level continuously, like in case of bulk material. Electrons can only occupy those discrete energy levels, and because of that, motion of electron is affected in a nanomaterial. In a semiconductor with a definite band gap, same thing can happen. Okay, in a semiconductor, you see there is a definite band gap in a bulk semiconductor, but energy levels in the conduction as well as the valence band can undergo similar discretization due to effect of nanosize. Am I clear? So, therefore, density of states, which is nothing but dN by dE, if you plot as a function of dimensionality like 3D, 2D, 1D or 0D, you will see discretizations happening from 2D to 0D. Very severe discretization happens in 0D. Electrons can occupy only very specific energy levels given by this delta function. You can see that spike at certain value of the energy levels, the density of undergoes shows a spike. So, therefore, electrons can occupy only these energy levels, they cannot occupy in between these energy levels. And because of this, electron motion is affected, energy transfer is affected significantly, right? So, this is the effect of dimensionality on the electronic motion, and this is known as a quantum confinement. Now, we must be thinking, what is it? Well, what is quantum confinement? Because this will keep on coming to us in optical or in electrical electronics properties also. So, electron confinement means change of electronic properties when the material is of sufficiently small size, typically of the order of 5 and less nanometers, 500 or less. Okay. As you know, this diagram at the bottom I have shown you earlier in the first 1 or 2 lectures. So, quantum confinement is observed when the size of particle is too small to be comparable with the wavelength of the electron. This is something which you must remember. This is only observed when the particle size is comparable with the wavelength of the electron, right? Same thing can happen with phonons also. If the phonon wavelength is comparable with the dimension of the material, this can be also important aspect for the thermal transport. And this is clear that this size effect will happen only when, or the size effect will be dominant only when the size will be 1 to 2 nanometers, preferably below 5 nanometers. This effect can be observed. So, normally the higher size between 100 to about 5 nanometers, we see effect of surface energy dominated aspects. We do not see much effect of quantum confinements. We only observe quantum confinements when sizes becomes much smaller, of the order of 1 to 2 nanometers. That is when the wavelengths of the electrons will be comparable with the dimensionality of the material. Now, you must be thinking, how does it happen? Well, so this is very similar to a particle in a box problem. Okay, very simple, and can be understood simply by invoking the concept of Heisenberg's uncertainty principle. What is it? Uncertainty principle states you very clearly that more precisely you know the position of a particle, more is the uncertainty in its momentum. Momentum is what? Momentum is P. P is m into V, right? And P is related to wavelength of the particle by the de Broglie's equation, right? That is lambda is equal to h by P. So, therefore, as you more spatially or space wise you confine and localize a particle, broader will be momentum or energy. That is right. Broader means what? The breadth of the momentum energy will be much larger. So, more you confine the particle to the dimensions, like if you have from 2d to 0d, the border will be range of momentum energy, and this is manifested as an increase in the average energy of electrons in the conduction band, that is increase of energy level spacing or larger band gap. Normally, band gap on a spherical quantum dots is increased from a bulk by 1 by r square, where r is the radius of the spherical nanoparticle. This has been observed. Well, so quantum confined nanostructure can be explained in a much better way. So, suppose you have a thin film, okay, then your only one dimensions are nanoscale, other two dimensions can be micron scale or anything more than 100 nanometers. So, this is a 1D nanomaterials. So, in electrons can easily move in two dimensions like x and y. So, therefore, kx and ky, that is the wave vectors of the x and y directions can be anything. Wave vector is what? Y square by lambda, and lambda is electron energy or momentum. So, therefore, electron can take any energy or any momentum in x and y directions, but in the z direction it cannot take, because it is confined. The dimension is smaller in the z directions. So, in case of 2D nanomaterial like a nanowire or nanotube, it is electrons are confined in two directions. So, it can freely move in one direction, like in the z direction in case of nanotubes. In 3D, like quantum dots or 2D and 0D nanomaterials, in all the three directions are confined actually. There electrons movements is confined in three directions. So, each further confinement direction changes a continuous component to a discrete component of k by quantum number n. Okay. How it is so? Well, let us consider particle in a box problem. Well, before that, let me just tell you, in a free electron theory, the outermost electrons are considered to take part in the conduction, right? And these electrons are assumed to be free to the move to the solid, and potentials which are periodic actually in a 3D materials due to nano cores or iron cores actually are almost constant. And potential energy of electron is not a function of the positions. Kinetic of electron is much lower than this potential energy, right? So, as you know, we know that, let us do this simple thing. According to de Broglie, lambda is equal to h by m omega mv, and therefore, if you consider the electronic mass, h is a value of what? H is a value of 6.62 10 to the power minus 34 joule second, and m of electron is 9.109 10 to the power minus 31 kg into V, and thus become 7.27 10 to the power minus 4 divided by V meter, correct? You can see that. So, now you can clearly see the V become like V is always of the order of velocity is very high. So, you can see lambda will be in the range of nanometers actually, by the way, because 10 to the minus 9 is meter, nanometers. So, V is 1000 kind of a meter per second. So, it will be lambda will be about 7 nanometers or so. So, not 1000, 10,000, no 10,000, 1 lakh actually. Then it will be, you can clearly calculate, it has to be 10 to the power minus 10 plus 5, then 10 to the minus 9. And we know that wave vector is always defined as twice phi by lambda. So, E is basically half mv square, we know that. So, I can write down then it is because h square by 8 pi square m into k square. This you know, right? This is very simple, correct? So, you can always define relativistic and non-relativistic things. So, by the way, in relativistic design it is h square k square by 8 pi square m, and many times we write these things as what? You can write this thing, I will erase it out. You can write that h square pi square into as a h cross. So, therefore, energy can be written in very simple way. E is h cross square, okay, by twice m into k square. What is h cross? H cross is nothing but twice h by 2 pi. That is what h cos is. So, the h square is h square by 4 pi square, and it is 8 pi square m. So, therefore, it becomes twice m. This is something which you should remember that, right. And the plot of these, if you plot E versus K, that you know that E versus K diagram looks like what? E versus K diagram will looks very simple like a parabola, right. K square. So, it is a parabolic equation. This is something all of you know that. So, if I plot this is my K and this is E, it will look like this kind of plot. Am I clear? This all of you should know that. So, as the lambda increases, what lambda increase, K decrease, right, and E also decrease. That is understandable. Am I clear? So, this is something which is very simple in a mathematical formalism. Now, let us consider the same problem in a particle in a box. Why you are talking about a confinement? Let us consider a box whose length is L in only one dimension, that is x dimension. So, it dimension varies from x equal to 0 to x equal to L, and we can always consider that for x less than equal to 0, V is infinity. You can see that V is infinity at x equal to 0, V is also infinity at x equal to L. So, that means what? You have a two, it is like a well with a two big barriers, okay, and you are sitting in the well. So, you cannot come out from that, right. That is what the meaning of this. So, we can always consider between x 0 to L, well, the potential V is 0, correct. More than x equal to L, potential is very high, less than equal to x, potential is also very high. So, we can write down this coordinate equation like this format, as you have seen here, h square by twice m 0 into d square psi by dx square in one dimension, this is equal to E psi, right. That is what it is. Okay. There is a potential energy, there is no kinetic energy part. Potential energy obviously depends on the double derivative of the psi. Now, if we apply boundary condition, psi is 0 at x equal to 0 and x equal to L, because V is infinity, the electron cannot stay there, you will see E n is coming to be at h cos n pi square divided by twice m 0 L square, right, where n is the principal quantum number, or values can be 1, 2, 3, right. So, you can clearly see that electron energy levels will be as a function of n, and you can actually plot the energy levels. So, that means what? Qualitative effect of quantum confinement very easily seen by plotting the wave function. So, once you know E n, then you can easily get wave function, and wave function is twice by L to the power half root of twice by L sine n pi x by L. This is nothing but a standing wave, right. So, energies are required to be quantized by the value of n, and psi changes from travelling wave to a standing wave. That is what is taught to you in your class 2 or maybe in the first year of your physics in the basic level of engineering or science, right. So, now you can clearly see that if I have a n equal to 1, then I have a standing wave like this, wavelength equal to L. If n equal to 2, it will be L by 2, n equal to 3, it will be L by 3, and so on. So, that means what? Energy levels are highly quantized, and E n therefore can be written as a pi square h square squares by twice m L square into n square, right. This is something which is always happen, and because this is one dimension, so we can write down nx, we can write down enx, right. That is very simple. So, because energy levels are quantized, electron can only take these energy levels, electron motion is dictated by the values of n. So, therefore, it cannot be continuous any further, right. So, L is the dimensional of the material. So, if you make L to be nanoscale, that means what? If it is a 2D nanomaterial, that means one of the dimensions are nanoscale, by the two dimensions are not nanoscale, then L becomes thickness of the thin films. So, then you can easily get the wavelengths of the electrons will follow this kind of things, right. Well, so we can do the same mathematics for 2D and 3D, right. So, in a 2D it will be nx square plus ny square, and in 3D it will be nx square plus ny square plus nj square, correct. Am I clear? Remember there, here m is the mass of the electron, okay. It is not 0 mass, it is relativistically corrected mass. L is the length or width of the confinement of the infinitely deep potential well. Nx, Nn, and Z are the principal quantum numbers in the x, y, z directions respectively. So, smaller dimension of nanostructure, a smaller value of L, it will be wider will be the separation between the energy levels, right. Am I clear? This is very clear. As the L become bigger, wider will be separation between these energy levels, right. You have energy levels for these different values of n will be separated much larger way. That is what you have seen in case of these energy levels which you see here at the both the valence band and the conduction band in the metal, they are because of these characteristics. Okay, you can have only those values of energy levels which are allowed, others are not allowed. Am I clear? Others, in other energy level, electron cannot stay. So, we come back to the same concept as the Heisenberg's uncertainty principle. The moment you define the spatial dimension very clearly, the uncertainty of momentum increases so much, it becomes very, very broad, energy becomes very broad. Okay. That is the concept which is applied here. So, now if it is very clear, same thing can be applied for phonons, right. Phonons can also undergo similar kind of things, right, similar kind of confinement effects. Okay, I am not going to discuss about that. So, the quantum confinement effects thus can be put in this way. In a bulk material, the density of states versus energy curves will be looking continuous. In a 2D, they will be like a step function. In a 1D, they are like a X-ray pattern, right, almost looks like. And in a 1D, sorry, in 0D, not 1D, this is 0D. In a 0D, they are like a Dirac delta functions. So, electrons can occupy only these energy levels. In between, they cannot stay. Similarly, electron cannot stay. Probability of finding electrons in these things are much smaller than the spikes. So, you can clearly see that a continuous curve is slowly baking into a discrete energy level. And this is same thing as shown here in a nice manner, the bulk to sheet to wire to dots. Okay. So, let us come back to the situation now. Okay, we will talk about these thin films little later. First, let me explain or let me reiterate for the case of 0D, 1D, and then we go to 2D. Well, so a good way of understanding this quantum confinement effects to consider the presence of nearby surfaces of 0D, 1D and 2D nanostructures. They can cause changes in the distribution of the phonon frequencies, okay. Like electron, it can phonon frequency will be affected also as a function of the phonon wavelength as well as appearance of surface modes. This process can lead to change in the velocities of the phonons. The phonons are traveling waves, so they are moving at a velocity. Phonons can interact with each other unlike the quantum, unlike the photons, and once they interact with each other, they will form a group velocity. This is similar to the ring of waves forming when you drop a stone into a water pool. Okay. So, hence on this basis, phonon bottleneck or the electron bottleneck and phonon bottleneck both will occur in a 0-dimensional nanomaterials. Okay. Why? Because electrons cannot move any directions, their energy levels are confined in all three directions. Only in peculiar fixed wavelengths or discrete energy levels, electrons can remain or the phonons can remain. And because of this, many of the 3D, 0D nanomaterials, even metallic, can be insulators. They will not be able to conduct heat at all. What happens in one-dimensional? In one-dimensional nanomaterials, 2 dimensions are nanoscale, 1 dimension is what? 1 dimension is non-nanoscale, like a carbon nanotubes. And it has been found that in carbon nanotubes, the conductivity can increase in the tube, the length of the tube to a very high value like 3000 watt per meter per Kelvin compared to the other 2 directions like in the plane of direction. So, you know nanotubes, right? They are like this. So, we are talking about thermal conductivity in this direction as compared to this or this, right. So, this direction, the z direction, thermal conductivity can have significantly higher, 5 to 6 times or 10 times higher than on the plane of the sheet or the tube. Okay. that is this surface. Now, it can be as high as 3000 watt per meter per Kelvin. As you know, for pure copper, the value of thermal conductivity is only 400 watt per Kelvin meter. Okay? And so therefore, there is a substantial increase of the thermal conductivity because of this confinement effects not taking place and the jet direction, because jet direction dimensions are very high. So phonons and electrons can easily find ways to move faster, and they can conduct heat very fast. But nanotubes may not have many free electrons available, but phonons will be contributing a lot for the thermal conductivity. So now, what about 0D nanomaterials? Now, 2D nanomaterial, not 0D. Let us talk about that. In 2D nanomaterials, you have great number of lot of interest are there, the thermal properties of the material, because you have large number of applications in terms of the handheld PCs, electronic cellular phones, everyday home appliances, or various modern medical devices, coatings for radiation shielding, wear resistance coating, thermal barriers, or even flat panel display like a TV or a computer screen. This is very important. Okay. So it should be, in this regard, we should distinguish between different types of 2D nanomaterials. One is 2D single layer nanomaterials with thickness in nanoscale. Okay, you have given, I have already asked a question in your mid-sem exam on that. Okay, or you can have multi-layer thin films composed of several nano layers. Okay, or you can have thin film comparison of collection of nanostructure units. Okay, these nanostructure thin film materials can be subdivided into nanocrystalline materials or nanoporous materials. So the moment you have, what's called multi-layer thin films, each layer grain structure can be nanoscale or micron scale, both are possible. The fact that each layer is of a thickness of nanometric scale, it is a nanomaterial. You can also have nanometric pores in the layers. So you have this 3 or 4 different types of situations. First one is single layer 2D nanomaterial. Then you have multi-layer nanomaterials in which you have several things. One is multi-layer nanomaterials in which the grain size in each layer is nanometric, or grain size layers is micrometric or micron scale, or you can have nanopores in each of the micron size grain materials, right. So all are possible. So as you know, nanoporous materials are used as a dielectric material in microelectronic industry because of their low dielectric constants. Okay, because the moment you use a pore, dielectric constant will go down. However, the thermal conductivity are also low, which can cause a serious problem for these dielectric materials. So let us start with the single layer nanometric materials, right. So this is what is shown here, the platinum bulk and platinum thin films of dimensions 15 nanometers and 28 nanometers. This is a data which has been published by a group of authors, okay, like Zhang et al. And Zhang et al. In 2005, applied physics, Chinese physics letter. Okay. So what do you see here? The thermal conductivity of the thin films are much lower than the bulk of platinum. Correct. So that means what? The thermal conductivity has substantially reduced in case of bulk, in case of thin films. And the second thing you see is that the thin film thickness decreases, the thermal conductivity also decreases. So compared to 20 nanometers, 15 nanometers, thin film has a lower thermal conductivity, right. That's what is the question is. Now why does it so? That's very simple. As the thickness decreases, the energy levels are getting confined, and therefore platinum is a metal, the majority transport will happen by electrons. So therefore electron energy levels gets confined in the thickness directions, and electron cannot easily move. Not only that, the moment you create a thin films, you have large number of grains, okay, nanocrystalline or microcrystalline grains compared to the bulk, and these grains will have gain boundaries. The gain boundaries will act as a scattering agent for the electrons. That means they will be not allowing the electrons to have a smooth passage. They will be acting as a scatterer. Like, very simple. You have a particle in the air, the light can get scattered easily, right. Same thing happens when you have a large number of grain boundaries in a material, the electrons while moving inside the grain material, they will be coming to contact to the grain boundary and get scattered and move in the other directions. So, therefore, while taking the heat in the right direction, they will be bringing the heat back, right. So, that is why the thermal conductivity decreases. This is first thing for the 2D single layer materials, right, observe. Now, what about multi-layer materials? Multi-layer thin films and materials with nanoscale grains. In that case, we need to consider also the interface between the layers, right. It is not only the grains within the layers, but also you have additional aspect called interface between the two layers, and this interface will act as also scatterer. Whether it is a scattering phonon or scattering electron, that is not only important, but they will act as a scatterer. So, additionally you have quantum confinements because of the small layers in each case, and with that you have effect of scattering because of interface between the each layers. So, this is because interface constitute a disruption of a regular crystal structure on which phonons can propagate. If a regular crystal structure, phonons can easily move, but the moment you have an interface, phonons will go and stuck there and they will scatter back. So, therefore, interface will separate two crystal of the same material which two regions have a different distribution of phonons. And on the other hand, interface can also separate two dissimilar materials like such a multi-layer structure for which two different materials have two different densities and also sound velocities. Phonons are like a, they move at a velocity of sound most of the cases. So, this effect is similar to electron transport in nanomaterials, and end result is presence of any interface provides scattering and therefore reduction of thermal conductivity. What do you see? This is the you can see in each cases thermal conductivity. This is undoped single layer, you can see this is doped single layer, this is a poly layer. Okay, forget about doped and undoped. Compared to single layer, poly layers have polycrystalline layers have lower thermal conductivity, much lower. It is 100 here watt per meter, it is about 10 or 15 or maybe 20 actually. So, therefore, there is a 5 times reduction of the thermal conductivity even across the large temperature range. Well, the effect of doping is serious, obviously, it will be seriously felt, and doping will lead to much change of the energy levels of the electrons, as you know, and that will affect the thermal conductivity. So, forecast of single crystal silicon monolayers which are embedded between two amorphous layers, a strong reduction in thermal conductivity with respect to bulk happen. This is the bulk. Okay, you see the bulk has a thermal conductivity of the order of almost 1000 at about 10 to 100 Kelvin degree Celsius, 100 Kelvin. Okay, so, but the same thing is reduced extensively the moment you have a single layer silicon. So, especially at low temperature, this effect is more pronounced for polycrystalline silicon thin films, right. Polycrystalline means polycrystalline layers. Okay. So, for its gain boundary will act as a scatterer over the surface of multi-layer scattering. It is additional scatterer. Gain boundary will act as additional scatterer on the top of multi-layers. Multi-layers, each layer will be acting separately. So, interface between the layers will act as scatterer, and within the layer you have polycrystalline grains. That grain boundaries also will act as scatterer. Am I clear? So, overall, the idea is to take different approaches to control the phonon transport in various regions of the phonon spectrum. So, high frequency phonons can be blocked by the alloy scattering because wavelengths are of the order of few atomic speaking. Okay. So, phonons can have different wavelengths, and so therefore, their scattering will depend upon what is the relative gain size of the materials. So, now comes the nanoporous material. The size effect determines the number of and the pores as well as the size. Okay. So, due to the porosity, these materials have very low permittivity and thermal conductivity also low, which that is why it is used in microelectric industry, right. But this can lead to increase in the temperature of the device and the circuit can fail. So, therefore, they are not considered good materials for applications. So, the problem is it is not theoretically understood how to treat these nanoscale pores for thermal transport. Okay, it is not clear, but nonetheless the pores are not good for the thermal transport, that is very clear to understand. Okay. So, hence as you can see here, the 2D nanomaterials, the effect of the dimension is very distinct and clear on the thermal conductivity, and this can be easily explained by considering three important aspects. First, the confinement effect because of electron or phonons. Second, the scattering effect. Single layer scattering is less, multi-layer scattering is more. Okay. Multi-layer, each between the two layers you have interface will act as scatterer. Secondly, even if you have polycrystalline grains in each layer, the grain boundaries will act as scatterer. So, that will further reduce the thermal conductivity. So, if you want to have a thermal barrier, you can do that. You can create a multi-layer structure, and then within each layer you can have nanocrystalline grains. So, substantially thermal conductivity will go down, and that is what is used. But you know, then you have a question of the stability of these grain structure comes into picture. As you increase the temperature of the material, the nanocrystalline grains will grow and their grain size will become very large, and hence the thermal conductivity will change. So, this aspect is important. So, that is why many people, actually many scientists, they do not go up very low size of grains in each layer, but they reduce the thickness of each layer substantially, and each layer act as a separate layer, so they do not interact much. So, that is something which is very important. You know, so in a nutshell, I discussed to you various aspects of thermal behavior, not only the thermal conductivity, but also very fundamental concept like electron confinements, phononic confinements, phonon motions, without going into much of mathematics. Okay. I know that too much of mathematics may not be good, because then it will you need to dig up a lot of literature to understand those mathematical equations, but fundamentally the concepts can be understood simply by following the book of Michael Ashby and others in the chapter 7 nicely given. So, with this I will stop here, and we will come back in the next class on the electrical properties. That is easy for me now, because I have already explained you the electronic confinement, and I will again explain you in a different manner, but electrical properties will be discussed subsequently. Then finally, I will talk about magnetic and optical properties, and then wind up the properties of materials. Okay. So, in next maybe 5-6 lectures, I will wind up the properties, and then we will talk about characterization of nanomaterials.